AdaBoost, which stands for Adaptive Boosting, is probably the most popular boosting meta-algorithm in common use. In contrast to the random forest discussed in the previous section, it combines weak learners sequentially to build a stronger learner. There are a number of variations on the algorithm. We're going to concentrate on the basic binary classification case. The approach does extend to multiple class problems, but there are a number of kind of fiddly details which would be a distraction here. One thing to note is that we're going to be using a different labeling convention for our binary predictions or outcomes. Whereas previously our outcome labels in the binary problem were 0 and 1, in this case we're going to label our negative class with a -1 instead of with a 0. So our labels are -1 and 1. Obviously, converting between these two labeling conventions is extremely straightforward or even trivial, but using the -1, 1 has certain advantages when developing the algorithms for AdaBoost, and also for some other models which we'll look at in future weeks. One nice feature of this convention is that it gives us a nice, neat, easy way to calculate the direction of updates according to whether answers are right or wrong. So if your labels are 1s and -1s and your predictions are 1s and -1s, then you can just multiply them together. All correct answers will have a result of 1, all incorrect answers will have a result of -1. We can slightly generalize this so it's not just y times y hat, but it's y times the scoring function that we use to decide what our prediction will be. This quantity, y times f of x, our scoring function, whatever that may happen to be, is known as the margin. And we'll see it in action today, and also it will be very useful when we come to talk about support vector machines next week. This use of 1s and -1s also makes the final aggregation across the models in our ensemble easier. We will want to be able to combine them in some way where the predictions from each model retain some kind of magnitude in the appropriate direction. If the labels are 0, we can't just multiply them because that will just cancel everything down to 0. With the -1 label, we can multiply that and that will just set the direction for the strength of the prediction. So AdaBoost is going to be using weak learners. What does that mean? Well, there isn't a single clear definition, but the idea is that they perform a bit better than chance, but maybe not very much better. In fact, for classic AdaBoost, the requirement is that they perform at better than 50% accuracy. This is one of the reasons why it's a bit fiddly to extend them to multi-class problems. 50% accuracy is random with 2 classes. With higher numbers of classes, the threshold for random prediction is lower, and you have to deal with that in some way, which we're not going to go into here. So a little bit better than 50% accuracy for a binary classification problem is really not very good, so you could legitimately describe those as weak. The advantage of weak learners is that they may be very cheap to train because they're not really trying very hard. So if you're building an ensemble out of these things, you might need a large number of them. It's advantageous for them to be really easy to train. It is possible to use AdaBoost with strong learners, but it's often not really so worthwhile. The classic weak learner used with AdaBoost, although you can use it with any underlying learner, is known as a decision stump. This, as the name might suggest, is just a very small decision tree. In fact, it's a decision tree with only one split. So it never recurses into the child nodes. These are easy and fast to train because you only have to find that single split and there's no recursion. However, for most data sets, having a single split is not really enough to do very much in the way of building your decision. And so, on the whole, the performance is likely to be pretty poor. So I'll first describe what the AdaBoost algorithm is and how you would implement it and show an example of it in action, and then we'll have a look at why it is that it works. Each of the learners for the AdaBoost ensemble will be trained on the same data set, but a set of weights will be applied to them to say which ones we care about most. So the thing that is being minimized for each learner individually is a weighted misclassification error, which looks like this. The weights define the importance attached to each observation. Initially, all of the samples are equally important. There is no previous history of successes or failures to draw on, and so the weights are initialized to 1 over n, the number of samples in the training set. We're generally going to aim for the weights to be normalized at each step, so they always add up to 1. So a single learner, a decision stump, or whatever underlying model is being used, is trained on the training set, and then its classification error comes out, weighted according to those different things. On the basis of that, it decides its single split in the case of a decision stump. Once the learner is fitted, it is assigned a prediction weight. That is to say, how much of the output prediction of the entire ensemble should be based on that one learner. That weight is calculated just based on its weighted prediction error, like this. Note that the weighted prediction error epsilon used to calculate the prediction weighting alpha is based only on the performance of this individual learner. It's not based on the performance of the entire ensemble. There is some sequential information collected as the training sequence proceeds, but this information accumulates in the sample weights. After each learner is trained, these sample weights are re-weighted according to the predictions of the most recent learner. There are 2 formulations commonly used for this. One only changes the weights of the samples that were classified incorrectly by the most recent learner. The other one recalculates the weights for all of the samples. These lead to slightly different numerical results, but they wind up converging to the same answer. After this reweighting has been applied, the weights are normalized so that they add up to 1 again. The overall effect here is that all of the samples that were classified incorrectly have their weights increased. The samples that were classified correctly are downweighted to be less important to the next classifier. This whole process is then repeated for as many weak learners as you care to add to the ensemble. Once the whole ensemble is trained, you have a bunch of learners and a bunch of associated prediction weights alpha. You throw away the sample weights, wi. They're just an artifact of the training and they're associated with the training samples, so you don't need them anymore. And then you just calculate your final prediction like this, using the weighted sum of the outputs of all of the classifiers as a scoring function. And then you apply a simple decision boundary at 0, which classifies any positive scoring example as a member of the positive class, any negative scoring example as a member of the negative class. So let's have a quick look at an example of this in action, going through a few steps of the process. Here is a simple binary dataset with 2 input features. At our first iteration, all the samples are equally weighted because we have no previous classifications to go on. The resulting decision stump boundary looks something like this. Obviously, the performance isn't great. There are some things wrong in both sides because it's only been able to make a single axis aligned split. We then calculate the weights associated with this new set of predictions. All of the samples that were correctly classified by that first split are down-weighted, shown here by smaller points in the plot, and the ones that were incorrectly classified are up-weighted, indicated by larger points in the plot. This reweighted dataset is then passed to be used for training to a new decision stump, which produces a new boundary like this. Not surprisingly, there are more errors this time, because in this case the split was focusing on the small number of wrongly classified examples from the first split. The samples are reweighted yet again, and another stump is trained. The samples are yet again reweighted, yet another stump is trained. Finally, we have 5 learners, each of which has learned a different boundary, and we put them together in a weighted sum and use the zero threshold decision function. We get a boundary that looks like this. This is obviously much better than any of the individual single axis aligned splits of any of the individual decision stumps that contribute to the ensemble. For more complicated data sets, you might need to learn a much more complicated decision boundary with many more weak learners contributing. So that was a pretty simple example, but the results were quite impressive. The decision boundary learned with only just 5 decision stumps was not bad at all. So how does AdaBoost do this? Why is it that it works at all? What AdaBoost is doing is fitting an additive prediction model based on a whole series of individual component classifiers. So the additive model looks like this. It first forms a score, which is the weighted sum of the individual predictions, and then it applies a simple thresholding decision boundary to the output. It will be notationally useful to consider this weighted sum as a scoring function f of the data. So AdaBoost is building up this scoring function one weighted classifier at a time, and it's doing so to minimize a loss function. At this point, we're going to introduce a new loss function, the exponential loss, which looks like this. In fact, it's just the exponential of the negative margin. The exponential loss is one of these smooth approximations for the 0-1 loss, which just tells us whether we're right or wrong. Unlike the 0-1 loss, which changes only at the point of going from being correct to being incorrect, the exponential loss varies smoothly across the margins and is sensitive to what that margin is. If the margin is more negative, then the prediction is more confidently wrong and the loss is higher. The key to AdaBoost is to take some existing ensemble and add a learner to it and make that learner be the optimal one with the optimal weight in order to improve the exponential loss of the entire ensemble. We can express this like this. We have an existing ensemble, which is a scoring function fk-1, which is a weighted sum of individual classifiers. The individual classifiers h each output only a +1 or a -1. So they are predicting actual labels rather than scores. What we want to find then is a new classifier hk, again predicting +1 or -1, and an associated prediction weight alpha k that minimize this expression. That is the exponential loss of the entire ensemble. If we just look at this summation that we want to minimize over, we can see that we are exponentiating a sum. That means we can split that into a product of 2 separate exponentials. The first of these 2 factors doesn't depend on h and alpha. Consequently, we can treat it as a set of constants with respect to the minimization at hand. There's a separate one of these for each of the training samples. We can conceptualize them as importances or weights applied to those samples, calculated like this. So we still need to minimize this to find the optimal classifier hk and also the associated prediction weight alpha k. Let's first consider the classifier, making the assumption that alpha is greater than 0. We can separate out the correct and incorrect cases in this sum into 2 separate summations. So in the first case, it's a sum over all of the correctly classified samples, and in the second, it's a sum over all of the incorrectly classified samples. So this is 2 disjoint sets of samples which together make up the entire training set. And for all of them, there is just some exponential multiplied by the sum of the weights. The e to the minus alpha and e to the alpha. We don't know what they are, but we know they're not going to vary. We can expand these sums by adding in all of the missing cases, the incorrect cases, into the first sum and simultaneously subtracting the same cases with the same weights from the second sum. That gives us this. So the first part of this expression, e to the minus alpha times the sum of all of the weights, again, does not depend on the classifier. And in fact, the coefficient in front of the second sum, e to the alpha minus e to the minus alpha, that also doesn't depend on the classifier. So the classifier that we're looking for is just the one that minimizes the summation itself. But this summation is just the weighted misclassification error. So the optimal classifier to add at each stage in AdaBoost turns out to be the one with the minimum weighted misclassification error, and that's exactly what our training process will produce. The one thing that remains to do is to calculate the prediction weighting alpha k. At this point, we assume we've fitted hk, and so we know what the correct and incorrect answers are. And so what we need to do is minimize this pair of sums here. E to the alpha times the sum of the wrongly classified weights plus e to the minus alpha times the sum of the rightly classified weights. We want to minimize this so we can differentiate it and set it to 0. The differentiation is straightforward because the only terms that depend on alpha are these two exponentials. We set those to 0, we can rearrange and get this expression here. This has the inconvenient exponentials in it, so let's just take the log of both sides. The result looks like this. Again, we can rearrange this, so we get 2 alpha k equals this difference of logarithms, but subtracting 2 logarithms is equivalent to taking the log of one divided by the other, and so we get an expression like this. 2 alpha k equals the log of the sum of the correctly classified weights over the sum of the incorrectly classified weights. That denominator, though, is just the weighted error rate, epsilon. Moreover, we have normalized the weights to sum to 1 at each step, and so the numerator is just 1 minus that weighted error rate. As a result, we get this value for our new prediction weight alpha. It's a half log 1 minus epsilon over epsilon. At this point, we're basically done. There are a few minor pedantic details which I've glossed over in terms of how to get from this to the specifics of the algorithm that I presented earlier. But all of the major components are there. We have sample weights which are updated that depend only on the ensemble to date. We have the optimization for the classifier, which depends only on the weighted misclassification error. And we have the prediction weighting, which depends also only on the weighted misclassification error. One thing to note about this expression for alpha is that earlier we assumed that alpha was greater than 0. That will only be the case if epsilon is greater than 0.5. That means that our learners have to have a greater than 50% accuracy, otherwise the whole thing falls over and the performance will get worse. AdaBoost is efficient and it's easy to use. It's widely applicable. As long as fairly weak criteria are met, you can use it. It's relatively turnkey. You need to choose K, the number of weak learners that you're going to use in your ensemble, but it's not super critical. Each of those is incremental to improve the performance, so you can just cut off at some threshold. It's not like it's going to make the difference between working and not working completely. The efficiency of an ensemble can be improved by pruning out the less contributing members, those with very low coefficients, for example. This concept of taking a weighted sum over an ensemble of classifiers is one that we will encounter again when we come to talk about neural networks. Next week, we'll see a model which brings together many of the things that we've talked about today and last week. It's both a linear model and also a non-parametric model. It uses basis expansion in new and exciting ways, and it depends heavily on the margin function or metric that we defined earlier on today.